Good afternoon or good morning, friends of TACO. Thank you for attending another TACO sponsored webinar. My name is Brett Zerba. I'm an applications engineer with TACO, and Rich Medairos, who will be doing the main presenting, and I work mostly on the commercial side for training, amongst other things. And I recognize quite a few names on the attendee list, so I know that you've sat in on many of these classes before. Before we get too far, let's go through the hand waving exercise. If you can see me, see Rich's screen, and oh, good, I see people already raising their hand. They think they do it before. David, thank you very much, and others. Martin and others already waving their hand. Thank you. That's excellent. So here's some of the initial statements. Number one, there are 3 handouts that are available for download. These are items that you can download right from our website, but I've saved you some time. Some of them will be the handouts that pertain to some of the products that Rich is going to be talking about. Some of the examples of this hydraulic separation that equipment can do for you. So keep that in mind. TACO equipment. TACO is celebrating its 100th year anniversary this year, as you can see. Very, very proud of that. It's quite a history. A privately held manufacturing company. We actually was started excuse me, in New Jersey, but we've been in Rhode Island for almost well over 90 years, probably over 95 years. So pretty proud of that fact. A privately held 3rd generation manufacturing firm in Rhode Island. The current owner is Johnny White, and many of you may have seen him or on TV or on YouTube or maybe at an ASHRAE event or something. He's quite a charismatic person. We are lucky to have him as our leader. His executive leadership team is led by Cheryl Merchant. She's our global CEO, and her staff have done a tremendous job keeping us in production throughout this COVID situation. And by the way, we are coming out with some 2021 TACO Tuesday schedule, so be on the alert for that. Hopefully, with any luck, well, maybe we'll only offer them for half the year, because then we'll start bringing people to our factory for some of the trainings that we used to do. So I got my fingers crossed on that, but who knows? Who knows where the light is at the end of the tunnel? So tomorrow, 24 hours after today's seminar, you will get an email, or you should get an email with access to the recording of today's webinar, and access to your PDH hour certificate if you need that and your state accepts it. So be on the alert for that. And if you don't get it, email the website or the link, and we'll make sure you get a copy of that. Today's presentation is on hydraulic separators. You know, in HVAC industry, we use those. Sometimes we don't think about them, and Rich is going to get into a lot more details about them. So you know, ask question, right? Most of you aren't shy about asking questions, so type in the area and ask the questions throughout, and I'll make sure I bring them in. I'll be moderating, Rich will be presenting, and we'll bring the questions to the forefront as we go. So I think that's all I have. You know, enjoy this month, all right? It's the last month of 2020, and it appears some good things are happening in the U.S. and in the world as far as COVID goes, hopefully. So let's keep our fingers crossed on that. And I truly believe, I'm an optimist, that the light is at the end of the tunnel, and let's all think that way. So Rich, take it away, my friend.
Well, thanks, Brett, for that great introduction. Just a few words about myself before we get started. My name is Rich Medairos. I'm one of the senior systems engineers here at TACO. I am a registered professional engineer. I specialize in the engineering design of HVAC systems, and I've been doing it for several years. So we're going to get directly into our presentation today. We're going to talk a little bit about what is a hydraulic separator. As I always like to say, where is a hydraulic separator used, how to size a separator, and then questions at the end. So what is a hydraulic separator? Well, a hydraulic separator, by any other name, is known in the industry. Some people call it a bridge, and we're actually going to show some diagrams, so don't worry so much about the terminology here, but just to be aware that it is in fact called by multiple names meaning the same thing. Other people might call it a decoupler. We've also referred to as zero pressure bypass, closely spaced T's, and twin T's. So all of these names refer to the same phenomenon, in which we refer to as a hydraulic separator. Okay, so I've got a little diagram here, and in my little diagram, I'm going to define a couple of things here. For a moment, I'm going to, let's grab a pen so I can write on the screen here. Here's my pen. I lied, it's not the pen. There's the pen. Okay, so let's look at the left side of the screen for a moment. We have this diagram on the left side, and we're going to call this left side of the screen here the primary loop. Primary loop. And then on the right side of the screen, let's see if I can do this without messing this up. On the right side of the screen, we're going to call this the secondary loop. So there's the primary. I'm using the letter P for primary and the letter S for secondary. And generally speaking, most people will refer to the primary loop as the source, either the chiller, the boiler, cooling tower, something like that. And the secondary loop will be the load side of the system. Now, sometimes people interchange these back and forth, but for our purpose today, we're going to stick with the most common terminology for primary, secondary loop. Okay. Now, with a little luck, I'll be able to erase that. Look at that. And this device right here, or this part of the primary, secondary loop, is where the decoupler is. And the most common terms are bridge or decoupler or hydraulic separator. And that's when we have a straight run of pipe, and then we have a tap to draw water off of that, and then a return line here. So let's look at a couple of different pumping scenarios. The very first one we'll take a look at is if, let's assume that the primary loop, and we're going to round these values off and call them 1,200 gallons per minute. So all of our discussion in this first part of the presentation will be based on 1,200 gallons per minute. So let's assume that our primary loop is delivering 1,200 gallons per minute. 1,200 gallons per minute goes around the corner right here. And for now, initially, we're going to say that the secondary loop pump is off, and we're not pumping any water in the secondary loop. And that means that the entire 1,200 gallons per minute is going to run across this bridge here. And so the flow across the bridge is not going to be zero. It's going to be equal to what we just said, 1,200 gallons per minute. The flow, in the secondary loop, because our secondary pump is off, is zero. So we'll put a zero over there. So all of the flow is running across here. Now, one of the characteristics of a bridge or a decoupler, sometimes again referred to as a zero pressure bypass. Hold on one second. A zero pressure bypass. And what that means is that the water flowing in the primary loop has no influence on the flow of water in the secondary loop. So the actual pressure, we're going back to 1,200 gallons per minute. So what's flowing in this direction here is 1,200 gallons per minute. And this pipe is sized appropriately so that the pressure drop, I'll just put a little pressure gauge over here. How's that one look, Brett?
Not bad, not bad, Rich. Not bad. A little squiggly.
A little squiggly.
You know what they look like? They look like the ones that I see when I go into mechanical rooms. All beat
up. All beat up and squiggly. So the actual pressure, let's assume in our oversimplified example here, let's say that this gauge is reading 10 PSI and this gauge is reading 10 PSI. Again, hold on one second. Today I feel like Joe Biden clearing his throat. Okay, so the pressure in both cases, as the water is flowing across here, is reading the same pressure, which means that the pressure drop from this connection over here to this connection over here, for all practical purposes, is negligible or is pretty close to zero. And so if we put a pressure gauge, whatever the pressure gauge is, we put here versus here, not accounting for elevation change, assume for a moment that this section of pipe is all at the same elevation, then the pressure should be reading the same value, and the pressure differential should be zero or pretty close to zero. So Brett, that's an important concept. I'm going to erase this in a moment, but I'm going to ask if anybody has any questions out there about the pressure drop across the bridge when there's no flow in the secondary loop.
I'm sure if someone does, they'll type it in. There is one question / statement. Does the term low loss header apply to hydraulic separators? I'm not sure you mentioned that at the beginning, but the answer is yes. And
yes,
maybe you want to clarify
some people
that.
will refer to as a low loss header. You can kind of think of this pipe here as a, I'll just kind of point out 3 sections of pipe, section 1, section 2, and section 3. You can think of this as a header, and the pressure drop across that header is negligible. So sometimes we use the term low loss, which means low pressure loss or no pressure change header. So yeah, that's another term that's used for the bridge decoupler, hydraulic separator, low loss header, and so on. So yeah, you get the idea. There's multiple names for the same thing, same phenomenon.
All set for questions.
Okay, so the next piece of the puzzle is that what if we had flow both in the primary loop, and again, I just, so we're all on the same page, so one on the left is primary, the one on the right is secondary. And let's assume that the flows are now equal, and again, I'm rounding this off, so I'm gonna make this 1,200 gallons per minute. Well, that's not the best looking tool in the world, is it? Let's try that again. 1,200 gallons per minute. 1,200. And this pump is also pumping 1,200 gallons. So that means that the water is coming around the corner here, 1,200 gallons per minute. And because the secondary pump is pumping 1,200 gallons per minute, it's going to draw off 1,200 gallons per minute in this direction. Eventually, it's going to go through the, satisfy the load in the building, and then it's going to come back here. And because not going to be any leaks in the system, nobody's drawing off any water, it's going to come back at 1,200 gallons per minute. And it's going to round the corner here to go back to our chiller, 1,200 gallons. And the flow this time across the bridge is 0 gallons per minute. So it's worth mentioning, even though it may be obvious, but let's just say it because, again, this is a low loss header or a decoupler. The flow across the bridge is 0 gallons per minute. And by default, if you have 0 gallons per minute across this point from here to here, then you meet the requirement of having 0 pressure drop. Okay, so that's when our primary flow, again, we'll put a P over here on the left side. That's when our primary flow and our secondary flow, we'll say the primary flow is equal to the secondary flow. Okay, so that's our second case, second situation. Now let's talk about the third. What if I have, again, my primary flow is 1,200 gallons per minute, but I'm not drawing off 100% of that flow, so I'm just going to arbitrarily make this 600 gallons per minute. If this is 600 gallons per minute, I know this seems a bit elementary, but there's something we're going to cover in a minute. So we're going to draw off 600 gallons per minute. If that's the case, we're going to return 600 gallons per minute. In a moment, I'm going to ask a couple of questions from the audience. If you could just type in the answer. Now, our system here, let's say that, let's assume for a moment that, let's say our return water temperature happens to be the same. We'll make it 56 degrees over here, just for the fun of it. 56 degrees Fahrenheit. So we have a 12 degree delta T. Okay, if we draw off 600 gallons per minute, then what goes across the bridge here is 600 gallons per minute. So we're going to get 600 plus the flow that came back from the secondary loop here. So we add those two together, this 600 plus the flow across the bridge. 600 plus 600 is 1200. We're back to 1200 over here. Okay, so now, based on the temperatures that I have in this system, if someone could type in, what is my supply water temperature at just before I get to the hydraulic separation or the bridge? What's my water temperature right there? Anybody want to type in and tell me
44 degrees is a lot of people are typing in here.
All right, 44. Now, if that's 44 degrees and there is a 12-degree rise, then this return water temperature is coming back here at 56 degrees. Well, that 56 degrees is mixing with that 44 because remember what's going across the bridge is 44 degrees. We said that's 44 in this direction, 44 in that direction, but 56 is now combining with 44. And because the flows are half of what they were before, the mix calculation, if you do the mix calculation out, you'll find out that the temperature is going to be halfway between these two. So since the differential is 12, that's 6. So this water temperature is going to come back at 50 degrees Fahrenheit right here. 50 degrees Fahrenheit. So that means that the chiller originally started off getting a return water temperature of 56 degrees Fahrenheit. Its return water temperature now is 50 degrees Fahrenheit. So that makes the chiller not as efficient as we'd like it to be. The building still gets the 44-degree water, but the return water temperature, mixed temperature at this point, is now going to be higher. Does anybody have any questions about that? Kind of an important concept.
Not specifically about that. There is a question about senseless pumps in its the secondary system.
So in this very simplified example, the primary flow remains constant. The primary flow is equal to 1,200 gallons per minute. So we could use a self-sensing pump in that arrangement if we chose to. The secondary flow is variable. And in this case, it's going to go from roughly 20% of the design flow. So that's about 240, roughly. A minimum of 240 to a maximum of 1,200. So we could use a self-sensing pump in the secondary part, and that would be a variable flow, variable speed. On the primary side, it would be constant flow, variable speed. Did that answer that question, Brett?
Yep.
So yes, we could use self-sensing pumps in this arrangement. Okay, so let's look at another case. Erase some of these lines, too many lines in there. So now let's look at, we had the primary flow equal to the secondary flow. We had the primary flow greater than the secondary flow. What would happen if the secondary flow was greater than the primary flow? Well, let's see what happens. Again, the primary flow is still 1,200 gallons per minute. And let's say for some unknown reason, don't have to worry about it so much right now. Let's say that the secondary flow is 1,800 gallons per minute. How could that be? Well, we go back to our bridge. It turns out, again, this 1,200 rounds the corner, but we're going to draw off 1,800. Well, how can we draw off 1,800 if we only have 1,200 available? Well, what we're going to do, we're going to cross out these values here for a moment. Our new value is 1,800. That means across this bridge in the opposite direction, now in this direction, we're going to have the difference between these two, or in our case, 600 gallons per minute. 600. So again, 1,800 comes back on the return side over here, but 600 runs in the opposite direction, and therefore 1,800 minus 600 is 1,200, so that's how we get 1,200 back to our primary loop. And now let's talk about the temperatures. Well, let's say what is the initial temperature that we start off with? And someone could type in, tell me what the temperature is at this point here. I'm going to put that up there in a minute. You're going to tell me what that is by typing it in. However, the supply water temperature this time out to the building is going to be something different. I'll give you that hint.
A lot of 44. A lot of 44 is being typed in, Rich.
44 up here, that's correct. We wind up with 44 there. But this temperature over here is now going to be a mix. And let's assume that it starts off, again, we'll just assume that this is 56 here. Let's X that out. If this is 56, now the return water temperature is 56, goes in at 44, comes back at 56. But that 56, since it's flowing in the opposite direction, it's going to turn out that it's going to be halfway between these two values here. So in other words, the return water temperature is now going to be, instead of 44, this is going to be 50 degrees Fahrenheit. Has anybody typed that in?
Yep. We got some 50s.
Yep, 50 degrees. So now look what happens. That 50 degree comes up here because this is 56. 56 goes in this direction because we're we're drawing off 600. So this is 56. So guess what? The chiller is happy, but the building is no longer happy because now we get a rise in temperature where before we had 44, our temperature to the building is now 50 degrees Fahrenheit.
Someone's questioning your 50. They said, I see a 48, a 42, 52, 48, a 52.
Well, actually, I might be incorrect. I'm glad that someone is observing that. So we can take the flow. It's actually going to be 1200 times, what did we say that was, 44?
Yep.
Plus 600 times, what did we say that was initially, 56? And then we divide that by our new flow of 1800. 48 degrees. Somebody was absolutely correct. It's 48 degrees. Yep. Sorry about that. I'm glad that someone's paying attention.
Excellent class. Woof.
Yeah, these guys are on the ball here. You guys are doing a great job. So this water temperature is now going to be 48. So at 48 degrees, so this is 48. It's higher than our original temperature. And so at 48 degrees, we may, in fact, not have a low enough temperature to provide the necessary dehumidification. So the bottom line here is that, and let me erase all this stuff. The bottom line is that when the secondary flow, let's say we'll put the secondary flow is greater than the primary flow, then we get a rise in temperature entering the building. And when we get a rise in temperature, we could have two issues. One, we could have a capacity issue. That remains to be seen, but we could also have a dehumidification issue. If the dehumidification characteristics were based on an entering water temperature 44 and we now have 48, we're not going to do as much dehumidification. So it's important to realize that in a primary-secondary loop, it's not only the flow gets influenced by the secondary pump, but also the temperature. So in some cases, the temperature will be equal to 44 degrees, and the return water temperature in our case, this is 56. So if the primary flow is equal to the secondary flow, the chiller is happy, the building is happy. When the primary flow is greater than the secondary flow, the building is happy, but the chiller is not happy. And then if for some reason in the last case, the secondary flow is greater than the primary flow, well, the chiller will be happy, but the building may not be. And that's one of the things that we have to be very careful of. And we have three cases. We're either going to have 0 gallons per minute across the bridge, we're going to have flow in this direction, or we're going to have flow in this direction. So that's some of the basic fundamental characteristics of a primary secondary loop. Any questions about that piece of the puzzle?
There's just a question/comment. It seems like the control for this would be a little complicated, but I'm sure there's some sequences of operation that are out there to figure it out.
Yeah, I'm trying to represent the simplest piping diagram to demonstrate the actual hydraulic separator or bridge. The actual control strategies I'm not going to address here, but there are multiple control strategies that you may want to consider. And I'm not trying to avoid the question. It's just that I'm focusing on the hydraulics rather than the controls. Okay. Let's move on now and talk about, here is another diagram. And in this diagram, let's just go back to my pen here. There it is. So over here is, again, the hydraulic separation. And we have a couple of different things we want to look at. Let's go back here. Yep. So we can replace the piping. So I'm going to try going back here a slide. Yeah. So here is the actual bridge itself. My pen again. Just like we showed in that first diagram, there's the bridge. And in this case, this is, sometimes I refer to this as field built. In other words, most engineers will specify how they want the hydraulic separator or bridge to be constructed. And it's a bit tricky because when it comes to designing the bridge, it may not get installed precisely the way you design it because of a variety of field conditions. So we want to talk about an alternative. Rather than designing it from scratch, another option is to put in a pre-engineered hydraulic separator. So a pre-engineered hydraulic separator looks a little bit like this guy over here. So it's pretty much exactly the same thing that we had before, only we have this device. Grab my pen. We have this device that's a pre-engineered product. And that's called a hydraulic separator. Now, Taco manufactures these. Other people manufacture hydraulic separators. It's basically it can be called a bridge, any number of things. The industry tends to call it a hydraulic separator when it's a pre-engineered product. And many manufacturers make these available along with Taco. So what does that hydraulic separator actually look like? Well, let's go here. And here is one called, the Taco brand name for this is called the 5900 Flex Balance. And just like the bridge that we had a moment ago, let's say that this is the primary side on the left, and this is the secondary side on the right. So here's the primary flow in here, and this primary flow comes out here. And remember our simple example of 1,200 gallons per minute. I'm going to keep referring to that. That's 1,200 gallons per minute. So on the secondary side, let's assume that in this case, I'm going to show a secondary pump. And in the secondary side, we'll say that the flow is 1,200 gallons per minute. So that means that the flow across the hydraulic separator is going to be equal to 0. Now, because this is a pre-engineered device, there's a whole bunch of dimensions here that are taken into consideration when the engineers design this in for factory manufacturing. What's important are things like the distance between the connections, both on the primary side and the secondary side. The other thing that's important is the distance, the overall height of the hydraulic separator, and the distance between the top and bottom relative to the connections. The other important thing is the diameter over here. And all of these things have to be taken into consideration when you design a pre-engineered product for the flow that you're looking for. There's also a baffle inside there to ensure that when the flow on the secondary side, in most classic examples, the flow on the secondary side will be less than or equal to the primary side, which we showed a couple of reasons why you might want to make sure that happens. In that case, we want to make sure that if the secondary flow is less than the primary flow, then you'll get some flow in this direction across the separator like that. So that is a pre-engineered hydraulic separator. It has an air vent at the top. And it's called a flex balance 5900 flex balance separator. Any questions about the first pre-engineered component?
There's a nice question / comment. I've worked on some projects where there's been some issues with the bridge or separation, the primary secondary loop. So if I use this component here, I shouldn't have any issues on any more of my projects, correct?
That's correct. And what you have to make sure is that it's sized properly. We will get into the sizing in a moment. So as long as it's sized properly and the piping is done properly, then it takes all the guesswork out. It's
He added the statement. He said, "Wish I had known before the project I worked on."
Yeah.
I don't blame him. I know what he means. I know
it's very challenging because we spend a lot of time on. Like I said earlier in the discussion, I spent the majority of my career on the consulting engineering side, and it's very frustrating because you spend a lot of time and effort designing something, and then it's not that anybody is being malicious. It's just that you wind up with these situations in the field, and it compromises the design, and you try to compensate for it, and sometimes it works and sometimes it doesn't. So yeah, it's a real challenge. But a pre-engineered device, it's not like they're going to take this in the field and then take a torch to it and cut it up in little pieces and weld it back together. That's not going to happen. But unfortunately, in piping, that's exactly what happens. Okay. All right, so erase this stuff here. All right, so let's look at a variation of this device. And the variation is called a 5900. Let's see, make sure my pen here. It's similar to the name before. This is called a 5900 Flex Balance Plus. We have the word plus in there. And that's because we are adding these baskets with Paul rings, both in the upper portion here and in the lower portion down here. And Paul rings, the name Paul comes from the inventor, some gentleman by the name, I don't know his first name. Maybe that's a good trivia question, Brett. You should find out the gentleman that invented these things. His last name was Paul, P-A-L-L. And the Paul rings allow us to convert the hydraulic separator into a dual function device. So not only does it act as a hydraulic separator, but it also now acts as an air and dirt separator. And it removes air at the microbubble size. And when we use microbubble, in this case, we're talking about 18 microns in diameter. Now, just to make sure everyone's on the same page, a micron is 1/1000th of an inch. 1/1000. So 1 micron would be 1,000th of an inch. 18 would be 18 thousandths of an inch. That's tiny. So
very tiny.
The hydraulic separator, whenever we add the Paul ring basket and the Paul rings, it converts it into a combination hydraulic separator and an air and dirt separator. So if someone is considering a hydraulic separator for their system, they may want to consider this device because instead of buying two separate devices, a hydraulic separator and an air and dirt separator, they can buy one device that does both functions into one. So that is something to consider. And there is a drain valve at the bottom. In this case, it's actually a drain tap that you can add a valve. And that's so you can blow out the dirt that's collected by the separator, and then there is an air vent at the top. This uses a float device. You can see the float right in there. So as air collects at the top, the float will drop down, opening the valve, the air escapes, and as the water comes up, it pushes the float up, closing the valve, keeping the water from escaping. So it's a very efficient device. Any questions about the 5900 Flex Balance Plus?
Nope. I do want to add though that one of the handouts is a test, the test data for this and shows how efficient it is. Actually, there is a question. Does it have to be installed vertically?
Yes, because you have to have the air vent at the top.
Yep.
And that's both the 5900 Flex Balance and the Flex Balance Plus. They both have air vents at the top. So they do have to be mounted vertically. Okay. So now let's talk about, I throw this in here because similar to what I hand sketched before, I want everyone to realize that when it comes to a pre-engineered device, that all of these dimensions are critical. The overall height, the distance between the connections and the top and the connections and the bottom. Now the diameter is also important, and the flange size connection, which we'll get to in a moment. So all of these are important relative to a pre-engineered device. All right. So this little chart is copied right from the the Flex Balance hydraulic separator catalog, and it's actually a sizing chart. So in our case, if you recall, we said our system had 1,200 gallons per minute. Actually, before I do this, let me go back to the diagram to kind of refresh your memory. Let's go back to the piping diagram. If you recall, on the piping diagram, in order to accommodate this flow of roughly 1,200 gallons per minute, we have a pipe size of approximately of 8 inches, not approximately, I'm sorry. So I have a little, I'm just looking up on my phone here just for a moment to see what that velocity is. So for 1,200 gallons per minute and an 8-inch pipe, that's about 7.7 feet per second. So intuitively, you might say, okay, I've got an 8-inch pipe, I'm running 1,200 gallons per minute, and that's going to be approximately 7.7 feet per second. So I'm going to select a hydraulic separator that's an 8-inch connection. Well, let me show you the selection chart for a moment, and you'll see that that's not the case. So if we go over here to this column right here where it says Optimum Flow, oh, can't I get my pen? There it is. Where it says Optimum Flow, we want to go to a flow that's equal to or greater than 1,200 gallons per minute. So I'm going to circle the first one that's above 1,200 gallons per minute. And if I look over here on the left-hand side, lo and behold, that's a 10-inch pipe size. So this is extremely important. You need to select the hydraulic separator based on this chart, and it's based on optimum flow. So even though the pipe size at 8 inches would be appropriate for, in this case, less than 8 feet per second for the pipe, the velocity has to be lower entering the hydraulic separator, in this case it has to be 10 inches, in order to accommodate the proper removal of air and the proper hydraulic separation between the primary and secondary loop. So that's how you size these. There's no other calculation that you can do. You have to come to this diagram, this table, and look at the optimum flow for your system and then select the flow. So let's assume for a moment we had 550 gallons per minute. At first you might say, well, 550, that would be good for a 6-inch. But in fact, 550, you'd have to go to the next size and you have to go to an 8-inch for that to work. Now, we do make standard sizes, as we said here, from 2-inch up to 12-inch. However, we can make hydraulic separators custom designed for much larger. And I have been out on job sites where the hydraulic separator has been as large as 36-inch pipe size connection. So we can make them quite large on a special order, but this is the information that's currently in our catalog for the 5900 Flex Balance and the Flex Balance Plus, same sizing chart. Any question, Brett, out there about sizing?
We have a couple questions. How come 10 and 12 have the same flow?
That's a great question. So what we know is that in some cases, let's just go back here. Let me erase that. Go back here. Yes. So in some cases, the 10-inch would have a maximum flow of 1409. The actual size of the separator, if you look at the diameter, they're both 30 inches. So this 30-inch can accommodate a 12-inch connection, because in some cases, someone may want to have a 12-inch connection, but it cannot exceed 1,409 gallons per minute. So that's more to accommodate the different size pipes that are out there, so that the 12-inch can't accommodate more flow than the 10-inch, but we offer it in a 12-inch to make it more convenient, because some people will have a 12-inch pipe connection rather than a 10-inch pipe connection. So it's more convenience than it is anything else.
Couple other
Did you say you
questions
had
here.
another question? Yep.
Are the air bubbles from the low water stream entrained into the high water stream?
Well, that's a great question. I'm not sure I know the answer to that. Let's go back to our diagram for a moment, Brett.
He's asking the same question for the dirt as well. But anyways.
Let's see. Let me go back and let's ask that question again. So what was the question again, Brett?
Are the air bubbles entrained in the high water stream from the low water stream?
From the high water stream to the low water stream. I'm not sure I understand the question. To be honest with you, I don't really, I'm not sure I understand the question, and I apologize.
Are bubbles from the low water stream entrained into the high water stream, I guess is the question. So if you have air bubbles on the bottom, will they go up into the high water stream? The dirt's going to fall down.
The dirt's going to fall down. Yes, the air will actually pass through the Paul rings in the upper basket, and they won't get caught there. Is that? I think that's what they're asking.
Yeah,
right?
and vice versa with the dirt. The dirt's got to go through.
No,
the dirt
because what actually, yeah, I think I understand what happened. I think I understand. So what's going on here is as water flows through the hydraulic separator and flows in and around the Paul rings, the air actually starts to collect at roughly 18 microns in diameter, but then the bubbles increase in physical size. It's kind of like, I don't know if you've ever blown bubbles. As a kid, you had the little soap bubble thing. If you blow the bubbles, the two bubbles collide with each other. Sometimes rather than breaking, they actually connect to each other and become a larger bubble. And that's actually what happens in these air and dirt separators. As the bubble first forms, it's very, very tiny, but then another bubble comes along and makes it slightly larger. And what actually makes the bubble rise in the device is the larger the bubble gets, it becomes more and more buoyant, and then suddenly it breaks free and goes up to the top. But it starts off as a little tiny 18 roughly microns, and then it keeps colliding with other bubbles larger and larger until it's buoyant enough to overcome the velocity that's inside the air and dirt separator. That's the scientific answer. I'm not sure if that's the answer to the question, but I think it is. Does that sound about right?
Yep. Do you need a minimum amount of straight pipe before the flange size, before entering the air separator?
Yes, you should have a minimum of 5 pipe diameters at the inlet and outlet of each of the connections. And that's to ensure uniform flow. The more uniform, the more, what's the word? Laminar. The more laminar the flow is as it enters and leaves the hydraulic separator, the phenomenon of zero pressure drop in the unit itself is accommodated. If you came in at a 90, say a short radius elbow at the inlet, let's go back one more slide so it might be a little easier to see. If you came in over here with a short radius elbow, let's say at the inlet of the primary side, you'd have so much turbulence that you could create an unwanted pressure drop in the hydraulic separator, inducing flow in the secondary loop where you don't want it. So we generally recommend that you have a minimum of 5 pipe diameters at the flange connection, not the pipe connection size, but the flange connection. So in our case, we said that this would be 10-inch over here, then 10 times 5 is 50-inch, which is roughly just under 4 feet. So that's, I'll just say it's roughly 4 feet. 4 feet. Now, if you had a smaller pipe, this is where you'd make the pipe reduction size over here from 10-inch to 8-inch. So you want that 10-inch to be 5 pipe diameters, which in our case, in this example, yeah, it's about 50 inches, 4 feet. Now, if I want to be really accurate, it's 4 feet 2 inches, right?
Yep.
I put the 4 feet in there. It's not that long a pipe. Okay. Any other questions?
No, go ahead.
All right. How are we doing for time? Oh, good. We're doing good. Okay, let's look at another device, which is called a multi-purpose tank. Now, you can get a multi-purpose tank configured as a hydraulic separator and also as an air and dirt separator with Paul rings. Now, in many systems, there needs to be a minimum volume of water in the system. So, for example, let's say that it's a boiler system, and for every roughly 10,000 BTU, roughly 10 to 12,000 BTUs per hour of boiler capacity. Let's say that they needed somewhere between 3 to 5 gallons per 12,000 BTU. So if you had a 12 million, let's just kind of do this out here. 12 million BTU system, divide that by 12,000 and multiply that by 5 gallons per 12,000. That means you'd need about a 5,000 gallon volume in your system. Well, that volume, by the way, is not just in the buffer tank, in this case, a buffer tank or multi-purpose tank, but it's also in the piping system. So if the piping system had a volume of, say, roughly 4,000 gallons, we would subtract that. So your buffer tank would have to be 1,000 gallons. So again, rather than putting in multiple devices, in order to keep the boiler from short cycling or the chiller from short cycling, you might consider putting in a buffer tank. Most manufacturers of the chillers and boilers would recommend that. And if your piping system, in our simplified example, allowed for 4,000 gallons, but the total gallonage that you needed was 5,000, then your tank would be roughly 1,000 gallons. Now, these tanks, multi-purpose tanks, work extremely well in terms of hydraulic separation for hot water systems. There is a certain amount of mixing of the water that takes place, which ultimately translates into mixing of the temperature. But for chilled water systems, we would have to make sure that the internal components of the tank had baffles to ensure that we did not have mixing. So you don't want to have your primary water mixing with your secondary water unanticipated, so that you wind up with the wrong outlet temperature. So multi-purpose tanks can function as not only a hydraulic separator, an air and dirt separator, that's 2 devices, but also as a 3rd device, it can function as a buffer tank or buffer storage tank for both chilled water and hot water systems. And again, when it's a chilled water system, please come back to the factory so that we can talk about the problem of mixing to make sure that the tank is outfitted properly with baffling, so we don't have a mixing problem with chilled water. Okay. So as promised, this is a fairly short and sweet presentation. Brett, do we have any final questions out there?
Yeah, you might have to go back to the picture or the cutaway of the 5900. Someone's asking, why is the, well, I mean, we'll see what picture we need. Why is the internal baffle relatively short and not longer? Does that show up?
Well, in this, maybe it's not that obvious, but in this case, the 5900 flex balance separator, the baffle runs the entire length, the vertical distance of the hydraulic separator.
Okay.
And I believe that's true. Yes. Hopefully that answered that.
Yeah, what is your recommendation on the secondary side? What distance would you recommend before you would put the pump?
Well, again, well, pumping is a little bit, the pumping, you need to think about the characteristics of the pump itself. So let's draw something out here. Let's do the primary. Let's let's again make this left side the primary and the right side the secondary, just to kind of stay with the same convention. There's the primary in, the primary out. Okay, so this would be, excuse me, this would be the secondary out. And eventually that's going to be connected to a pump. Well, I shouldn't have put that. No, I kind of screwed that up, put the S in the wrong direction. But anyway, so that's going to eventually be connected to a pump. So you have to look at the requirements of the pump and also the requirements of hydraulic separator. In general, this distance from here to the suction side of the pump wants to be somewhere between 5 to 10 pipe diameters. 5 to 10 diameters, DIA. That looks more, I don't know if that's a D. I'll try it again, Brett. DIA. DIA.
EIO?
DIEIO. 5 to 10 pipe diameters. That would be ideal for the hydraulic separator, and that would be ideal for the pump. However, the problem here comes in that the diameter of the hydraulic separator may not be the same pipe size as the pump, in which case that becomes a separate problem. Let's assume that the hydraulic separator had a 10-inch connection and the suction side of the pump, and I'm just kind of making this up. Let's say the suction side of the pump had 12 inches. Well, it would be the 12-inch that would be dictated in terms of the pipe diameter. So in other words, you would use, let's say you wanted to go at 5 pipe diameters, 5 times 12 would be 60 inches between these two. Hopefully that makes some sense to somebody. Any questions about that?
No, I think that answered it. So these flex balancers, how will that help maintain the temperature between primary and secondary?
Okay, so these are pre-engineered devices, and they're designed specifically to allow the water not to mix when you don't want it to mix. In other words, again, our ideal condition is when the primary is equal to or greater than, I'm sorry, I said it backwards. When the primary is, yeah, I said it correctly. The primary is equal to or greater than, equal to or greater than the secondary. And under that situation, if the primary is equal to the secondary, then there won't be any flow. There'll be zero flow across the bridge in this direction here. When the primary is greater than the secondary, then you'll get some flow across the bridge. And whatever flow you get across that bridge wants to be approximately the pressure drop, the delta P. Oops, I didn't leave myself enough room. The delta P wants to be approximately equal to 0 whenever there's flow across the bridge. I think I answered half that question.
Yeah, yeah, controls and it's pre-engineered, so you're not going to get the crisscrossing of flows.
That's correct, right? Because remember, it's the pre-engineered component it's critical in terms of the overall length relative to what the diameter is also. So these are critical dimensions. That's why it's pre-engineered, to make sure it works properly. If you're designing it yourself, you're taking a bit of a risk in terms of, you know, what the component sizes need to be.
I mean, we always think it's just as easy as 2 closely spaced tees, but that may not necessarily be the case, you know.
That's right. I mean, in some cases, if the tees are placed, the concept of closely spaced tees was that the closer the tees were, the lower the pressure drop was across the bridge. So let me just sketch that out here. Don't know what we're talking about. So again, here is our primary manifold, sometimes a manifold, and here's a T over here going out to the secondary side. There's a T right there. And I'm just going to arbitrarily draw one over here too. So there's a T right there. It's kind of an oblong T. Okay, if I make this distance relatively short, then the pressure drop across here is going to be negligible. But if I make the distance too short, I'll get a tremendous amount of turbulence over here, and I may get mixing when I don't want mixing. So the distance between the T's has to create a pressure drop that is close to 0, which is where the term closely spaced teeth comes from. But at the other hand, it also has to have a far enough distance relative to the diameter of the pipe, this diameter right here, so that you don't wind up with unanticipated mixing. So it's not that easy if you're designing it yourself. What most people do is they'll dramatically oversize this pipe. Let's assume that this main happens to be 12 inches. I'm making up a number here. And the bridge itself, they might size that at 16 inches and then make the T's far enough away so that there is no unanticipated mixing and the pressure drop is negligible. But you know, that's a lot of calculating and not necessarily predictable. That's why we try to recommend staying with a pre-engineered device. Takes all the guesswork out.
One last question, Master. What is the difference between a 2-port buffer tank with baffles and a 4-port buffer tank for hydraulic separation?
Great question. So let's go back to our multi-purpose tank for a moment. Here. And when I get the picture, let's ask the question again, Brett, when I get to the picture here. So if it only had 2 connections, right?
Yep.
So let's assume that it had a connection here. Let's say there was an inlet connection here and an outlet connection down here. Let's just throw it down here for a moment. And let's say these connections didn't exist. If that's the case, it's just a buffer tank. And it's not.
It's like an inline buffer tank, right? I mean,
correct. Yeah. Right. It's not until you put all 4 connections in here that you create as it's shown in this diagram. We have the inlet primary here and the outlet for the primary side, and then the outlet for the secondary side and the inlet for the secondary side. It's not until you have these connections in that configuration that it becomes a hydraulic separator.
You answered that one, my friend.
Okay, great. So hopefully, before I turn it back to Brett, I'm going to say thank you very much for listening to our presentation this afternoon. Hopefully you learned something about hydraulic separators. Let's base these lines here. Ta-da, I erased the lines. Look at that. So hopefully you learned something about hydraulic separator. Let me just go back and say that hydraulic separators are commonly used in primary, secondary circuits. And the main function of a hydraulic separator is to ensure that the flow in the primary or the secondary loop doesn't cause unanticipated flows in the adjacent loop. So in other words, the flow on the primary side, when the secondary is not flowing, does not provide any ghost flows or unanticipated flows. So that's the main purpose of a hydraulic separator. And it's not the same as hydraulic isolation. Hydraulic isolation is typically done with a heat exchanger, either a plate and frame or shell and tube. That's when the 2 quantities of water never mix with each other. They might transfer the heat, but they don't physically mix. But a hydraulic separator, they always mix, but you don't want to have unanticipated flows or ghost flows from the primary to the secondary loop. So that's it. So at this point, thank you so much. If we have any last minute questions, I'd be happy to field them. If not, I'm going to turn it over to you, Brett, and say thank you and be safe out there.
A lot of good thank yous, although there is one comment about your current screen. They're wondering what MPSH means.
Well, there's an excellent observation. There's a typo. So I cut and paste this questions from my NPSH, which stands for Net Positive Suction Head presentation, into my hydraulic separation. And it's one of these weird things that I've been doing this for a period of time, and I never realized that.
See, I tell you, this has been a great audience, a fantastic audience.
This has been great. And so what I really need to do is just change this. Oh,
you know what? Thank you, everybody. Yes, excellent.
Let me see if I spelled that correctly, Brett.
Yeah, it's got 2 A's, not the.
Did I sell it? Oops.
Yes. Yeah. A lot of thank yous, Rich. Yes, you did. A lot of thank yous. So excellent job as usual. And everybody, appreciate your time. We know how valuable it is. Look for the schedule for next year. You know, we'll do one a month for commercial, one a month for wholesale. So they'll be out there. We'll be coming out with that hopefully in the next, well, pretty soon. And then look for your email tomorrow, their handouts. And other than that, take care, everybody. Stay safe. Happy holidays. Actually, Merry Christmas, Happy New Year, Happy Holidays, and enjoy the rest of the year. And let's get on to 2021. I can't wait for it. Take care, everybody. Bye.
Take care, folks.
Yep, everyone's welcome. Thank you.